We're in the shop, all lit up for Halloween. My son recently got an e-bike. He got a Rad Power Radrunner 2, and it comes stock with a 48 volt, 14 amp hour battery, and he loves it just the way it is. But me being a dad and being me, I know he could use something a little more powerful. So I'm going to build him a 52 volt, 25 amp hour battery, and that should give him about twice the range and maybe even a little bit higher top speed, depending on how it goes. And it's going to be about twice the size of the stock battery, but I think I can still make it fit in the frame. And I'm going to build it out of these. This is an 18650 lithium ion cell. Kind of looks like a AA battery, but a little bit bigger. And I need a little over 100 of these in various combinations to get to that capacity and voltage. And I figured I'd start with some theory, show you how you select these batteries, what sort of combination you get them in, and then show you how it's built. I built e-bike batteries before, but I never really documented the process. And I want to try out my new camera rig here. I got an iPhone 15 Pro Max. Looks pretty good, right? Yeah, so as we build it, we'll get to see some cool tools like this. This is a battery welder, pretty neat. And if you don't really care about the theory and just want to skip to the good stuff, you can check out the chapter markers below. All right, I think that's it. Oh, but as always, safety first. All right, let's do a little bit of battery theory here. So one of these cells, these 18650 lithium ion cells, you'll generally see them referred to by their nominal voltage, which is usually going to see 3.6 or 3.7 volts. That's sort of the amount of charge they have when they're 50% full. And the full range goes from about 2.8 or 2.9, 3.0 volts, you'll see different numbers for the low end, up to 4.2 volts on the high end. So if you go any lower than that or any higher than that, you damage the cell. But we'll look at a device later called the BMS, the Battery Management System, and that's going to manage charging and discharging to make sure that we do not damage the cells. And again, generally when you see these calculations, you'll see them referred to against the nominal voltage, which we'll consider 3.7. So if you were to take a multimeter, test one of these batteries, 3.7 volts. The capacity is 3,200 milliamp hours. That's not quite as easy to test with one of these. You can hook something up, a load, and you can measure how much current is going through them, and you'll see a total, which will hopefully be around 3,200 milliamp hours as advertised. So I got to get from 3.7 volts up to 52 volts, and 3,200 milliamp hours up to 25,000 milliamp hours. So how are we going to do that? So it turns out if you wire batteries in series like this, end to end, you start multiplying the voltages. So you've got double the batteries, you got double the voltage, 7.4 volts, same capacity though, 3,200 milliamp hours. If we had a third one, now we're up to 11.1 volts, same capacity. So I not only want more voltage, I want more capacity as well. And how do I get that? So then I do what's called wiring them in parallel. So now if you were to test these two wires here that joined up the positives and negatives, you'd see the original voltage, 3.7 volts, but now the capacity is doubled, 6,400 milliamp hours. And same thing if we added a third, same voltage, we're up to 9,600 milliamp hours for the capacity though. And then you can combine series and parallel and you end up with something like this. So in this case, we've got 4 in series, which gives us 14.8 volts, and we've got 3 in parallel, which gives us that 9,600 milliamp hours. And you'll notice they're connected not only on the ends, but in between here. So all the nodes are connected. Now, this layout, you'll see we have quite a while to go to get up to my desired voltage and capacity. So this layout is going to start getting pretty unwieldy, right? You're going to end up with a bunch of batteries like this, which is not ideal to mount on a bicycle. So what if we sort of bend these in on each other and we end up with a shape like this? So you'll see positive and negative sort of alternate, and the current's going to flow through like that. But you'll see we still have one big overriding negative and one big overriding positive. And if you measure those two, that's going to be your final voltage. So you can combine that with the parallel layout, and now they're going series this way and parallel this way. So this is the most efficient shape to mount on a bike. You'll end up with like a nice little rectangle. So how many of these do I need to get to my desired voltage and capacity? Turns out I need 14 in series. 3.7 volts times 14 gets me to 51.8, which is just about 52. You see these numbers are a little nebulous. It's never quite the exact voltage you're looking for, but it's close. And then to get to the capacity we need, we're going to need 8 of these. So 3,200 milliamp hours times 8 gets us 25,600 milliamp hours. And you'll see this referred to, this sort of series versus parallel counts referred to like this. In this case, I'm building a 14S 8P battery. 14 in series, 8 in parallel. And if you multiply those two numbers together, you get 112. So we'll need 112 of these cells to build this battery. We're almost ready to start building, but first, let's take a look at why I chose these cells. These are available with all kinds of different specs. So let's see why I went with these particular ones. So here's where I got my batteries. This is the 18650batterystore.com. I went with these EVE 33Vs, and you can see the capacity there, 3,200 milliamp hours, But then there's also this 10 amp number. What is that? So if we scroll down here, we can see that's the continuous discharge rating. So that's, you can continuously draw 10 amps from one of these batteries. And generally, you don't want to go anywhere near this limit. It is possible, but there's a thing called voltage drop, where instead of having the maximum 4.2 volts, when you're pulling 10 amps, that voltage might drop to 3.2. So you're not getting anywhere near the voltage you think you're going to get. So you can stick like half of that or below, you're good. And you figure, okay, well, how do I know what does this need to be for my use case? And in the case of the e-bike, you're looking at what kind of amperage the controller draws. So on the Radrunner 2, the stock controller will draw a maximum of 25 amps. And there's upgraded controllers that'll draw up to 35 amps. And you're looking at this number and saying, oh man, this is nowhere near 35 amps. But you have to remember these batteries are wired in parallel, and the parallel then stacks these amp ratings. So you can actually pull from an 8P pack, you can pull 80 amps continuous discharge. Again, you don't want to go near that. You want to stick to half. So figure 40 amps, that's well above our 35 amp rating, right? Each battery is only pulling 4 3/8 of an amp or so. So that should be well within that range. And let's compare this to some other batteries on here. Why did I go with this one? Well, if you look at the famous Samsung 30Q, the capacity here is only 3,000 milliamp, but it has a 15 amp continuous rating. So you might have some kind of a use case where you need to be able to draw a lot more current, and you have to go with a battery like this, even though the capacity isn't as high. If you compare that to the 35E, now this has another 500 milliamp hour of capacity, 3,500, but it only can draw 8 amps continuous. So something to keep in mind. And then I'm looking at the price. These are $6 per cell. This is $6 per cell. These were normally $6, but they're on sale right now for $3. So I went with these ones. And when you're looking at these, you want to make sure you get the flat top, which is what we're looking at, not the button top. Button top kind of looks more like a classical AA battery with a little nubbin. We do not want those. You'll see the brackets and these nickel strips that we use to weld on do not work with this style. You need the flat top style. And this site has some interesting categories here. So you can go in here and look at, you want a pack build and you want high capacity is what you're worried about. So you're going to look into here, and these are going to be all their high capacity ones, 3,200, 3,500, 3,450. There's even a 3,500 that does have a 10 amp draw, but you see that's $8 per cell. Or you can go in here and say, you know what, I don't need a ton of high capacity. I just want the cheapest ones they got, and you can look in here. So right now, because these are on sale, this is in this category. But you have one of these guys here where it's only 2,000 milliamp hour. But look at this charge. You could do pull 30 amps from that battery. Wouldn't last very long, 2,000, and they're cheap, $225. Yeah, so this is the most popular size. It's 18650, and that number refers to the actual size of the cell. It's 18 millimeters in diameter and 65 millimeters tall. And there's another popular size that's 21700. I don't know that some of the equipment, some of these brackets that we're going to use to hold the battery together, I'm not sure that they're all available in this size. They probably are, but I haven't really dug into them. I stick with the 18650. But these are, because they're bigger, they generally have a higher capacity. So you see there's 4,500 milliamp hour. Some of these are the same. There's 3,000 milliamp, and there's 35 amps draw. There's 4,000. I think I've even seen a 5,000. Yeah, there's a 5,000 milliamp hour one. So if you really need a lot of capacity, that's the way to go. All right, here's everything we need to build the pack. Surprisingly, not that much stuff. We've got our batteries. They generally come in a box like this of 100, and then I had a few more than that, right? The 112, so a couple extra around the side there. We've got this pack bracket, 18650 pack bracket. So what this is these hold the batteries like so, and then you put the top on. It holds them in there really well and presents these little nubs here for welding, and ends up with a really nice structurally strong unit. Really holds it together well. And this bracket is available in all these different little sizes, 1x1, 1x2, 1x3. These are actually 4x5s together, and there's a couple little extra spots. So I think I had some 3s that I had to fill in. And it has these little bracket systems that kind of like lock together. So you can see, you just slide them together. Really nice. And then here's that BMS I mentioned, the battery management system. And this is a 14S. This handles 35 amps. So it'll definitely cover the stock controller and should cover an upgraded controller as well. I think I might let a little bit more than 35 pass now and then if it needs to. But if it stops the battery output because of if a new controller is drawing too much current, I'll just have to upgrade that, put a new one in. This is nickel strip, nickel ladder. I call this 2P because it'll put 2 of them in parallel. And what happens is when you put this bracket on, this is how you weld. This ladder will fit right in these little spots like this. And you'll weld along the batteries there. Like that. We'll see that in a moment. This is some Kapton tape, Kapton. just non-conductive tape, kind of tape down some of these loose wires we'll have flopping around. And then I got my voltmeter, and I have the voltmeter here because generally when you get these cells, you want to test them to make sure the voltages are all very similar. When you put a bunch of these in parallel, we've got our parallel strips going this way. As soon as you weld the conductor on here, you're going to weld the strip on, these batteries will all try to rush and charge each other if one of them is low. So if you had one of these that's at 3.2, one of these at 4.2, a ton of current is going to run in there and try to charge that one battery, and that can be very dangerous. So generally you want to make sure that all the ones in these parallel strips are very similar voltages, and these probably will be because they're right from the factory. But a lot of these guys build these packs, they salvage batteries from like laptop packs, and there's no telling what the voltages will be. So you'll want to test them all and then kind of group them in similar voltage units. And if you have a couple outliers that are super high, super low, you have to charge them up or discharge them to kind of get them in the same as the other group. So I'm going to work on testing these out. I'm not expecting them to be anything crazy. This one right now is at 3.46, and I bet they're all going to be pretty similar. Yep, 3.46. So I'll go through and test these, and then we'll pick back up after they're all tested. As expected, all the voltages on these are very similar, so we can go ahead and start populating our bracket. And we're going to put these in the parallel rows, and each parallel row is going to face the same direction. So these are all going to be up. And then this next row is all going to be down. And remember our illustration, the voltage is going to go through like this, the current. So we're just going to go through here and keep alternating rows. There we go. And then it's just a matter of putting the top on. Let's make sure we got minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, we're alternating good. Get our top on. This is always interesting to get these to line up. Oh, that went on pretty easily. And you can see now when it's done, it's a pretty good solid brick. It has a little bit of a twist to it. Actually, once we weld on the nickel strip, it'll get real stable. So it's looking good. All right, on to the next step. Next up, we're going to cut our nickel strips to fit. So we're going to lay one across here, and I want to leave a little tab sticking out on one end. And this stuff is so thin you can cut this with scissors. And I believe this is 0.15 millimeters thick. And there's ampere ratings for this as to how much amps these can carry. And I think I'm going to double these up just in case. So I'll weld one on, and then I'll weld another strip on top of it. So I'm going to go down here now. So I need to cut 1, 2, 3, 4, 5, 6, 7. Double that, 14. And then the other side, we're not going to do it like this. We're going to offset by 1. So this will get a single line down here, and then it'll be nickel strips in between. So 1, 2, 3, 4, 5, 6. So 14 on the other side, 12 on this side, and then we'll make 2 single strips for here. You want to be careful when shopping for nickel strip because a lot of them are steel with just a nickel coating, which doesn't conduct nearly as well. You want pure nickel strip, you'll usually see it listed that way. And you can test it. You can put it into a solution of salt water, and if it rusts, it is steel. All right, nickel strip's cut, ready for the next step. Ready to start welding here. I've got our battery welder, and each pulse here is set to 30 joules. That's 1 pulse of the weld to be that much power. And got our battery in our bracket. And normally I would start over here, but it's kind of in the way of everything here for the camera, so I'm going to start over 1. And you want to make sure when you got your ladder here, it's not like offset. You see it's laying on the plastic and not really flush. You want to make sure it's really good in between there. And I have the welder set that all I need to do is hold it on. And right now it's set to 2 seconds before it'll actually do a pulse. I'll turn that down here in a minute, make it a little bit faster, but just for demonstration. There's also it comes with a foot pedal, so if you don't want to have this automatic mode, you can manually trigger it with your foot. And you might hear some fan noise come on as the power comes on for the welder. I'll try to minimize that. All right, so we're gonna start here. We'll start here on the minus on this side. And the way this ladder is, it has a little gap between, so I'm just gonna straddle that gap. And you'll see as I hold electrodes on, as soon as they both touch, you'll hear a rising tone, boop, boop, and then it fires. And there we go. I'll just give it a little tug, make sure. So that's the whole battery itself moving in there, but the weld is on there really good. And then I like to do 2 on each, so I'll do another one here. And now let me turn this trigger delay down just to speed this up a little bit. I'll move it down to like 0.4 of a second here. And I'll just kind of go down the whole row here of the minuses. And just give it some nice firm pressure to make sure it really gets a good weld on there. And I can see the charger is off screen here, but you know, every time I do a pulse, it draws a little bit of juice to charge these capacitors back up, and I'm ready to go again. And as I go and do a bunch of these cables will start getting warm, so they're fine right now, but we'll see how far I can get before it gets too warm. And also, if you press and hold afterwards, you'll see this display. I'll give you some statistics, so I'll do a hold here and see. So we let it know it was okay. That was the 9th pulse. It was 30 joules. Went for 18 milliseconds, and it was, what did that said there, 1100 amps in one shot. Pretty good. And then it'll also give us the final temperature, I think, of the unit. So if I need to let it cool off, let's see, 18, 1200 amps. Resistance 31C. So we're good. I'm gonna keep going. Okay, that whole row's done. It goes pretty fast once you go. And it's so, oh, there's the fan kicking in. And people, we like this method instead of soldering, because soldering adds so much heat and it's a lot of heat soaking into the battery, which isn't really good for it. But this is like so quick and instantaneous, there's no heat at all. When I touch these, it's completely cool. All right, so now we'll go down the positive row here. Oh, so I might not have had very good contact there on that one. Try that again. I can feel these are starting to get warm. Oh, I had a bad one there. It actually looks like it burned right through the nickel on that one. Ah. Let me continue on. My electrodes are getting a little burned looking here. Make sure I got my good pressure. Yes, I think that was the problem here, is I wasn't really, the pressure was a little bit off on that one side. There we go. That's better. So there we go, that row's all done. And then my little tab sticking out, I don't know if you can see that on the camera, that'll be where the BMS is hooked up. Cables are a little warm, but not too bad. Start in the next row here. And I want to make sure my tab is in the back, not the front. I'm going to give myself some extra down pressure, makes I have really good contact there. These are starting to get pretty warm. Let's see what the actual temperature of the unit is here. I'll hold it this time and see the temperature readout. $18, 1200 joule, 1200 amps, resistance 1.2, 35. So the unit itself isn't getting that much warmer, but these cables are starting to get warm. It's just getting a little uncomfortable to touch right here. It's getting kind of toasty. And you can see that the wires actually move. There's so much current coming through here, it moves the wires. Pretty warm. Okay, so I might let this sit for a minute and just cool these off, but then we'll continue on here. All right, so that's that side completely done. So we're gonna flip it over. And now this is where we wanna start getting careful. So previously we were only connecting 2 rows at a time. So remember 3.7, 3.7, 7.4 total. So we're making like little 7.4 groups. Now as we start stacking them on here, it's gonna start multiplying. So every time we put another one on, that's like doubling that voltage. So we wanna be a little more careful. Not anything crazy, just we want to make sure we don't have any random pieces of metal laying around. It's going to fall and bridge a couple of these things. They say the human skin response is your skin's dry enough up to like 50 volts or so before you start worried about getting shocked, and this is going to be 52 volts, so we're getting close to where you could, in theory, get shocked by your own battery pack. So we just want to take our time and make sure we're doing what we think we're doing, and again, make sure there's no random stuff that's going to randomly bridge anything. So again, we're not going to go, if we did this, that'd be very bad because we'd be creating 2 short circuits. So we can make sure we're going to offset by 1. So just to make sure that doesn't happen, I'm going to do my single first. I'll do my single across here, and then we'll go, and then it's going to end with a single. All right, so let's do a test now. So now we've got 4 in series. We're going down and then up and then down and then up. So if we test between here, we should be around 14 volts or so. Probably a little less because remember, instead of the nominal 3.7, these were about 3.4 from the factory. So there we go, we're at 13.8, 13.9 almost. So we're getting there. All right, so now if we test between our positive and our negative, we should be at around 52 volts. So what is that, 48.4? Yeah. And the charge is a little bit lower, but once we charge up, that'll be good. All right, so I have to do a second layer of nickel strip, and then we're ready to hook up the BMS. Here's our battery pack, all complete. We've got our double layer of nickel strips, and here's all those little tabs. So what are those tabs for? So if we look at the BMS, remember all these wires coming off. Each of these wires connects to one of these tabs in sequence down the pack, and it allows the BMS to monitor the voltage of each of these parallel rows. So if we start here at the pack's minus, right, this will be 0 volts, and then 3.7, 7.4, 11.1, 14.6, and it climbs as you go down. And that lets the BMS do something called balancing, where it can balance the charge between each of these rows. So after a lot of charge-discharge cycles, one of these rows could be at 4.2 at maximum charge, and another one here is at 4.1. Ideally, you want everything at 4.2. So this allows it to sort of monitor each row and bleed off some voltage here and there to make sure everything gets charged up to 4.2. And then there's 2 big wires here. There's a P minus and a B minus. The B minus connects to the battery's minus, so this is going to wrap around and connect on there. And then the P minus is where you pull your charge from. So this is probably going to run down. The way this is going to mount on the bike, the motor connector is here at the bottom. So I'll run the minus down, and then I'll run the positive over to a connector here to discharge the pack. And then to charge it, I'm probably going to 3D print a little bracket here and have the little charging port. So another P plus, or I guess it's a B plus, will come up and connect up to the connector along with another branch off of this, and that'll be where you charge it from. So the next step is to sand up these so I can get solder to stick to them. So I'll rough these up just a little bit, and then we'll solder a wire on each one going down the pack. And then once we connect these big guys, then we're just about done. And we'll just heat shrink the whole pack, and it'll be ready for install. Okay, we're just about ready to start soldering up these wires here. So I've got my BMS. I just put a piece of Kapton tape just to kind of hold it there temporarily as I'm wiring things up. I'll leave the wires a little bit long probably, just in case I want to move that. I've got some flux paste, help my solder flow a little better. Got my solder, got my soldering gun warming up. Got my wire strippers. And I got a little piece of sandpaper. So what we'll do here is for each tab, we'll kind of scratch it up a little bit, give the solder something to stick to. And this is the ground starting with, so it's going to start with this wire. And I'll figure out if it's going to be absolutely the final position to be something like that, but I'll leave just a little bit of extra. And we'll trim this. And we'll strip it. And then I'll put just a little bit of solder on it. And we'll give ourselves a nice little pool of solder for this to stick to. And it doesn't need much. And then we'll kind of bend this over a little bit. And we'll just solder this wire on. That's it. So the first one's done, and then I'll just go down the road here, and I got to make sure I alternate. I'll probably do all these top ones first, just this is the position the battery's in. So I'll do every other wire here, and then we'll flip over and do the other ones. So like this next one, the next one in line would go down to this one, but we're going to skip that one and do this one. This one's going to come up here. There we go. And then we'll know we did the wires right because the very last wire here was the very last one there. So that counting, I think, turned out okay. So now I'll flip it over to wire up the other side, and then I'll just do a double check to make sure I got all these correct. Okay, all the balance wires are connected. I double checked that they're going to the proper ones. So now we got to wire up the minus, the B minus. Stick that up here. Scuff that up a little bit. I notched out a piece of the plastic there, so that way that wire can like nest in there, and it's going to sit just like that. So I tinned this up, so this guy's ready to go. So let's add some solder here. Okay, it looks pretty good. Let's see about the positive end. All right, we're at the positive end of the battery, and I think what I'm going to do is this is where the battery mounts to the bike, and the motor connectors sort of down here. So I'm going to wire this in, have the connector hanging off the bottom like this, and then I'll hook the minus up. This will run up battery to the P minus wire on the BMS. And it's going to be it would be a little unsafe to wire these up and then have two dangling wires of 52 volts floating around. So I think what I'm going to do is connect them to the connector first, and then wire them to the battery. And for that, we're using the XT60 connector. These are sort of become a standard in the e-bike world. And there's also like an XT30 and XT90, and the number refers to how many amps. So this can handle 60 amps, so well above our 35 amp potential maximum. And the way these are generally wired is the male end will be the end that's providing power. So the male end is going to come on here, and then I'll wire up the female end into the bike. And then the charging port will also have a female end, and you can actually chain batteries together and multiply your capacity. Realized another way I could solder this up without putting the heat right on these batteries is I can solder this wire to a little piece of strip first and then weld this strip to the battery. So I'm going to do that. Big old pool of solder here. Okay, that looks like that's down there pretty good. So now we're ready to wire up the negative from the connector up to the BMS. And I've got the other wire here going to the charge port, again 12 gauge, and I'm going to use these crimping terminal lugs here. So rather than try to solder all three of these together, I'm just going to crimp them together. That's pretty good. And then we'll heat shrink it. All right, that looks pretty good. And then we'll see about connecting the charging cable. But if we did this right, we should be able to check this connector and see what our voltage is at. Oh, there we go. There's our 48. So the pack's ready to discharge. We just have to hook up the charging port and we can charge it up. Try it. After some experimentation, I decided to do the same thing with the positive lead on the charging connector. And that's put one of these crimp connectors in here. So I split this cable, put in a crimp connector, and then I ran a secondary cord all the way up here to the top. And I didn't get a chance to solder them into the connector, so I was going to have these bare wires flopping around, so I just stuck a piece of electrical tape on the end there, make sure they don't spark against something. But both the positive and negative are going to get trimmed here, and they're going to basically face off the edge there. I went to my computer and designed a little housing for the charging connector, and then I went and 3D printed it. That is looking pretty good. Let's hook up to power and see if it charges. So I've got a charger. This is a 5 amp charger, and I put a XT60 on the end. Got the voltmeter hooked up to the discharge port, monitoring our output voltage. So when I plug this in, hopefully the charger starts charging, one of these LEDs goes out, and then we should see the voltage on here slowly start climbing. Fan turned on, LED went out. Here we're at 49.0, and then we'll see if that starts climbing up. There we go, 49.1. So I'll let that sit for a little bit, and we'll do a little time lapse here and watch that charge up a little. To get a sense of the ranges of various voltage batteries when they're 0% full versus 100% full, you might only have access to the voltage itself. You don't really have a real battery meter. This chart is amazing. It shows you every voltage from 0 to 100% for 36 volt, 48 volt, 52 volt batteries. All right, that took about 9 minutes to go 1 volt. So you can see when you take power off, it kind of drops back down again. It kind of settles down. So, all right, I'm gonna shrink wrap this, and then I gotta build a bracket for the bike. I'm ready for heat shrink. I put a couple layers of EVA foam here. This bike has no suspension, and my son likes to ride off curbs and stuff. So rather than have this being like this battery just sitting on a metal support, it has a little bit of cushiony foam there. So on the back of the frame and then the bottom. And this EVA foam just comes in these big sheets. You can cut it with scissors. And the heat shrink comes like this. I only have this blue right now, but I'll probably get some black and then redo this. Usually you think of the heat shrink as the little stuff, the little pieces for wires, but yeah, it comes in these huge sheets like this. So then we gotta try to slide this on here, and we'll heat it up. So I'll try to center it in there. And the heat shrink really only shrinks this way. This way it doesn't shrink much. These ends will kind of curl over. And depending on how tight it gets, I might trim it a little bit. But that way this will leave this core at the bottom. It's going to wrap around to plug in. Got a nice little brick. Trim a little bit of that, but yeah. All right, let's trim it up and see how it looks. Looks pretty good. All right, let's install that on the bike, see how it works. Got to wire in an XT60 into the bike connector. So this is the connector going to the controller. So there we go. How to build an e-bike battery. Another project in the books. But you know, I can't help but think that bike could use a little more power. Hey, Jack.